Okay, so thank you everyone for coming and thank you for the kind introduction. So my name is Niklas. I'm a PhD student under supervision of Professor Münstermann at RWTH Aachen, and I'm working with MPU aero engines. And today I want to present a new model or our new work on a weakest link approach for crack initiation modeling informed by crystal plasticity. Okay. So the part in question in my case is a blade used in an aero engine, in the turbine section of an aero engine. And it is made from a polycrystalline superalloy, so a nickel-based alloy, produced in a standard casting process. And I've roughly sketched here the crack initiation mode in this alloy. So we first get dislocation movement at stress concentrators, which are usually then casting pores, leading to the accumulation of strain and slip bands, and in turn then the crack initiation along those bands. And as you can probably imagine, this process has strong interactions with the local microstructure. So the way we are modeling this is using a micromechanical approach. So what we're doing is we're calculating the local mechanical response using crystal plasticity simulations. And from the result of those simulations, we can derive a quantity called a fatigue indicator parameter that we are able to correlate to the lifetime. And it is a field quantity, so we get it for every material point. And then by looking at the largest of these fatigue indicator parameters in our configuration, we can determine the lifetime of that configuration. The problem with this naive approach when it comes to porosity, however, especially on the part scale, is the fact that we have to do a very fine discretization around the stress concentrators, so around the pores. We have to have a very fine mesh. And combined with the wish to have all the porosity modeled, this leads very fast to computationally extremely expensive simulations due to the number of elements in the simulation. So we had to come up with a different approach. And what we did is we introduced statistical submodeling on top of the purely mechanical modeling of the crystal plasticity. And that statistical model is based on the weakest link idea, which is the notion that our material behaves like a chain with discrete chain links that where the crack initiation can occur. And in this analogy, the pores, I've marked them here as P1 to Pn. So those are all the potential crack initiation sites in our alloy. And for the statistical submodel, now we first have to create this an instantiation of this chain, so a random porosity, a virtual porosity. And we do so by acquiring statistics or acquiring experimental data about the porosity using, for example, micro-CT. From this, we derive a defect size distribution. And we then do random Monte Carlo drawing to get to a random instantiation of this chain. And what we also do is we do a binning step in between here. The reason this is important may become apparent in the next step, because for certain bins, so for certain defect sizes in this simple example, we have pre-computed damage distribution using the crystal plasticity. And so for every pore size here, for every bin, we do another drawing from those damage distributions here. And then we get a bunch of fibs, and the largest of those fibs then gives us the lifetime of our weakest link. And this gives us a point on the SN curve, or even multiple points, so a whole Euler curve, if we have pre-computed damage results for more than one loading. And by repeating this process over and over here in the middle, we get multiple curves from which we can then derive also statistical properties about our fatigue curve, and therefore find our design curves. So for example, with a 90% survival rate. Yeah, so the advantages of this are we capture statistics of crack initiation. We do so at a reduced computational cost, and due to the because it allows us for pre-computing of the computationally expensive crystal plasticity, we can do real-time assessment. So yeah, I will now start with the results. So the first thing we wanted to confirm is that our model assumptions are actually correct. To do so, what we compared the results of modeling multiple pores explicitly using crystal plasticity, and compared this to the case where we modeled only single pores explicitly with CP, and coupled this with the presented weakest link model. And yeah, this is how the result looks like. So what you're seeing is a cumulative distribution function of the acquired results. On the x-axis, you see the fib. On the y-axis, you see the chance of finding a fib smaller or equal than that value in the distribution. And the dotted lines here indicate the results that were acquired by CP of single pores. And the solid lines are the distributions that we get for pore agglomerates. With the red line, in this case, the pore agglomerate is explicitly modeled using crystal plasticity. And the blue line is the proposed approach. Applied to the single pore values. And so the first thing that we're seeing when we look only at the median, so basically the intercept here with the intersect of those points here, is the fact that, as expected, the larger single pores here, they have a higher expected median damage value. And another very important thing, though, is the fact that the agglomerate shows a higher damage value than the largest single pore here. So this kind of implies that also the smaller pores play a role, and we can't completely disregard them when we want to model our agglomerate. And another thing that we're seeing is the fact that the blue and the red curves nicely align. So yes, the weakest link model is a good way of approximating the results. Yeah. Now we come to the application of such a model. So what we did is we captured porosity parameters, like I said, using MicroCity. Calculated a database of fatigue indicator parameters, and then applied the presented model to 3 porosity volume fractions, the one being the measured one, and then 2 hypothetical cases where we halved and doubled the distribution, the volume percentage of the pores. And those are the results that you're seeing here. So this time, the dotted lines indicated Weibull functions that we fitted to the data. One important thing that you're seeing is as we have a higher porosity volume fraction, the expected fib increases, which is kind of expected on the one hand. But what's interesting about this is the fact that the underlying porosity distribution here is actually the same in all cases. The only difference is the number of pores that we are drawing here. And so this means this is a purely statistical effect, and that can't be replicated using standard deterministic approaches. And in turn, this also means that our model is able to capture size effects, which we can see in reality when we increase, for example, the volume of the tested specimen. Yeah, so last but not least, conclusion and outlook. I've shown that crack initiation is a highly statistical process once we introduce microstructure into the modeling, because then the smaller pores can't be neglected in general. The presented model here allows to use CP simulations to assess porosity on the part scale, and the model is able to explicitly capture the statistical effects that are appearing. And next steps in our work we would like to find a continuous description of the model response to get rid of the discreteness due to the binning. We want to incorporate pore interactions, and we want to incorporate pore parameters other than size, especially morphology. Yes, that was it from my side. Thank you very much for your attention. And if you have any questions, feel free to tell them now or approach me anyway.